In this presentation, I will talk about instrumental variables. The outline of this presentation will be first to define endogeneity problem, then talk about the instrumental variables and their properties. Then I will discuss the IV estimation and then the two-stage least squares estimation. And I will talk about it both in terms of simple regression and multiple regression, and then I will finish up with testing for endogeneity. First, what is an endogeneity problem? That is when we have the independent variable being correlated with the error term. So one of the problems with an endogeneity problems is that we would actually have coefficients that would be biased and inconsistent. So that is a frequent problem in economics and econometrics. There are several sources of endogeneity, and two of them we have discussed previously here. One of them is omitted variables when the independent variables are not observed and they end up in the error term. So the error term would be correlated with the independent variables. And the second source of endogeneity could be when there is a measurement error that can cause correlation between the mismeasured variable and the error term. So a few solutions for endogeneity. The best possible solution is if there is omitted variable, then find and include the unobserved variable in the model. Now, if such variable is not available, then a second best solution would be to find and include a proxy variable in the model instead that would be standing in place of the unobserved variable. We also discussed using fixed effects estimator with panel data, and doing so would eliminate the individual specific effects that may be correlated with the error term. And this lecture would talk about instrumental variables method, which would replace the endogenous variable with a predicted value that only has exogenous information, so making this predicted value being effectively an exogenous variable. So let's provide a definition. An instrumental variable, also called instrument or IV, is a variable that is used in a regression to correct for the endogeneity problem. So if we have a dependent variable y and endogenous variable x that is correlated with the error term, an instrument z would be such a variable that is related to the endogenous variable x but does not belong in the model for y and is not correlated with the error term. So again, a good property of the instrument z is that it is not in the model for y and it's not related with the error term, but of course it's related to the endogenous variable x. So here is a simple regression model where we have y regressed on x. So our dependent variable y regressed on x. So if x is exogenous, in other terms, if it's not correlated with the error term, so x and u are not correlated, then the covariance of x and u would be equal to 0. So if we actually substitute in the covariance of x and u, so we have the covariance of x, and then this is the expression of u if we rearrange this equation here. So if we have the covariance of x, and this is basically the expression for u, and then we open up these parentheses, what we would have here is the covariance of x and y. Covariance of x with the constant would be 0, and then we would have the covariance of x and minus beta 1 here. And so this is what we have, minus beta 1, and the covariance of x and x would be the variance of x. So now, if this covariance is, if this expression is equal to 0, then we can find an expression for beta 1, which will be the covariance of x and y divided by the variance of x. So this is what we have here. So if you recognize the covariance of x and y divided by the variance of x, that is actually the expression for an OLS coefficient. And the covariance of x and y is the summation of x minus x bar, y minus y bar. This is over all the I observations. And here in the denominator, we have the summation of x minus x bar times x minus x bar. That's the formula for the variance of x. So if x is exogenous, then the OLS estimator would work and it will be unbiased and consistent. So this is a review of how we do OLS estimation when we have x being exogenous. Now let's suppose we have the same model of y on x, but if x is endogenous this time, which means it's correlated with the error term, then the covariance of x and u will not be equal to 0. And so if that's not equal to 0, what we need to do is find an instrument z that is not correlated with the error term u. So basically covariance of z and u equals 0. So now we don't have that for x because that covariance is not equal to 0, but we can find an instrument that is not correlated with the error term. So now we can do uh, the same procedure for the instrument. So the covariance of z and u this time, we can replace u with the expression from here and then open the parentheses. So now we have the covariance of x and y minus the covariance of z and constant is 0. And then the covariance of z and x multiplied by this minus beta 1. And so now if we want to find an expression for beta 1, that would basically be the covariance of z and y divided by the covariance of z and x. That's what we have here. Or that is basically the covariance of z and y is the same as z minus z bar times y minus y bar, the summation of that. And the covariance of z and x is the summation of z minus z bar and x minus x bar. So now this beta is beta IV. This is the IV formula for how we can estimate a coefficient. The nice property is that this estimated coefficient will be unbiased and consistent. And so notice what is the difference here from what we have here in the previous formula. So in the previous formula here we have the covariance of x and y, not z and y. And here we have the covariance of x and x, which was the variance of x. So one thing to conclude here is that if x is exogenous, it can serve as its own instrument. So z would be equal to x. And then this IV estimate, if z is its own instrument, um, if if x is its own instrument, if it's exogenous, we would have the covariance of x and y divided by the covariance of x and x. That would basically be the formulas that we have on the previous slide. And basically what would happen here is that the IV estimate would be identical to the OLS estimate. So one thing that we're finding is that when we have exogenous variable x, even if we apply the IV estimation here, because x can serve as its own instrument, basically we're going to find very, very similar results to the OLS results. So if the coefficients that we find with IV are very similar to the coefficients that we can find with OLS, that could tell us that perhaps we have the case of exogeneity and we don't need to use instrumental variables. We would have a formal test later on, but initially we can just inspect how close these two coefficients are using the OLS and the IV coefficient here. Now, what are the properties of a good instrument Z? It should have three properties. The first one is that the instrument Z does not appear in the original regression model. So if this is the regression model that we have here, notice that Z is not included in here. So Z should not be a direct determinant of Y. Now, the second property is that the instrument Z would be correlated with the endogenous variable X so that the covariance of Z and X would be not be equal to 0. So in other ways, there's going to be a linear relationship between X and Z. And in order for them to be related, this would imply that this coefficient that we have here, delta 1, would be significantly different from 0. So we want this coefficient to be significantly different from 0, so there is a relationship between x and z. And the final property that we have of an IV is that an instrument Z would be uncorrelated with the error term U. So the covariance between Z and U would be equal to 0. And we need this property because that was the problem that we're trying to solve, that the covariance of X and U does not equal to 0. So we need to find an instrument Z for which this covariance is equal to 0. So again, in summary, the property of a good instrument is that the instrument does not appear in the original regression model. The instrument is correlated with the endogenous variable, but it is not correlated with the error term. Now, we talked about the IV estimation using the formulas, but here is an alternative way in which we can obtain coefficients, and that is called two-stage least squares, or as abbreviated is 2SLS. And basically that's almost an equivalent procedure to obtain the coefficients. So how would we do this? So here is a regression model, and we can do an OLS estimation on it, of course. But if x is endogenous, then this coefficient beta 1 that is estimated with OLS will be biased. So the alternative is to do two-stage least squares. In the first stage, what we will do here is regress x, which is our endogenous variable here, on an instrument z, and that would be the regression of the endogenous variable on the instrument z. So then what we would do is we would get the predicted value x hat here. So this x hat is now the predicted value coming up from this equation, and these are the coefficients here. So now notice that we don't have y here, the dependent variable in the first stage of the two-stage least squares. We have x, the endogenous variable. So it's a bit unusual for us to see x hat because we usually don't do that to independent variables. But because now x serves as a dependent variable, we can get the predicted value here for x, which is x hat. Now, the predicted value here would contain only exogenous information from the instrument Z. Why? Because we assume Z is exogenous, and therefore, using this equation here, x hat would only have the exogenous information from Z. It would not have any endogenous information in it. In other ways, if you look in this equation here, if Z is exogenous, this means that if we have any endogeneity, we would leave this in the error term here, in here. So we have the exogeneity, and anything that's endogenous would be left in the error term. Okay, so the first stage of the two-stage least squares is to estimate regression of x on z, get the predicted value x hat, and the second stage of the two-stage least squares, we would be doing almost the same as the original equation here. However, we would be replacing x with x hat. So now this would be the predicted values for the endogenous variable. Now that only has exogenous information from this instrument z here. So if we estimate these second stage of the two-stage least squares, what we're going to find is that this beta 1 coefficient would be unbiased because this x hat only obtains exogenous information that is not correlated with the error term u. Again, the reason for that is because we're using a z instrument that only contains exogenous information, and therefore x hat would only contain exogenous information. So now this would be the procedure to calculate a two-stage least squares coefficient. So again, in the first stage, we regress the endogenous variable on the instrument, get the predicted values, and then in the second stage, replace the endogenous variable with the predicted value and estimate this regression to find the coefficient. So a side note here on the standard errors when we do two-stage least squares. What we're going to see is that the standard errors would need to be corrected. And the reason for that is in the OLS model, we have that the variance of beta 1 is sigma squared divided by SST. Sigma square is the variance of the error term u, and SST is the sum of squares total, is the total variation for x. So we have seen this formula when we talked about simple regression. Now, how we need to correct this formula is we need to divide by this r square between x and z. And so this r square between x and z is the r square from the regression of x on z. And so in order for us to calculate the standard errors, if we have here the variance, we would be taking the square root and we would be obtaining basically the standard errors for the two-stage least squares. So notice here what we are finding. So the variance of beta 1 with two-stage least squares that we have here is exactly the same as the variance of the OLS right here. This expression, so that's the variance of the beta hat OLS, and then divided by this term here, the r square of the regression of x on z. So if we take that the square root of that, what we're going to find is that the square root of variance is the standard error. This is the standard error, and then we have the square root of the r square. So now we have an expression for how the standard errors of the two-stage least squares coefficients are related to the standard errors of the OLS. Now, because we have this number here, r squared is less than 1, what we're going to find is because this denominator is less than 1, we would have that this whole expression would be greater than the standard error for the OLS. So we would have that the standard errors for the two-stage least squares are greater than the standard errors for the OLS. Um, and so that's one of the drawbacks of two-stage least squares is because we're going to have higher standard errors. If we have higher standard errors, this would mean that we would find less significance of the coefficients because the coefficients, um, in order to find significance of the coefficients, we need to take the coefficient divided by the standard error. If we have higher standard error, we would have lower t-statistics and therefore we would be having less significance. So one implication here is that the weaker the relationship between x and z, it would actually result in lower r squared. And what we're going to see is if we have lower r squared, we would find a higher variance here, higher variance of the two-stage least squares coefficients, and we would have less significance. So again, that's one of the issues with two-stage least squares is that even though we are correcting for the bias that otherwise we are going to find, and that's our first priority, we want to correct for that bias by using the two-stage least squares procedure. One of the drawbacks is that actually the standard errors and the variances would be higher, leading to less significance of the two-stage least squares estimates. Okay, so we talked about the IV estimation and the two-stage least squares. So if there is only one endogenous variable and one instrument, then the two-stage least squares estimates, and that was doing the two-stage least squares procedure, which is replacing x with x hat that is based on z. So that um, x hat based on z, that would be the first stage least squares. And the second stage least squares would be replacing x with x hat in the equation for y. So this approach here will be the same as obtaining the IV estimates, which was using the formula, the covariance of z and y divided by the covariance of z and x. So basically, we would obtain exactly the same coefficients, whether we use the two-stage least squares estimates or the IV estimates. Now, We can also do the two-stage least squares estimation if there's more than one endogenous variable, and we need to have at least as many instruments for each endogenous variable. Now, let's consider an example here. So we are going to have a model for log wages that are explained by education. But education is endogenous. So we would be using here father's education as an instrument for education. Now, why is father's education a good instrument for education? Well, it's so because it has satisfies the three properties of a good instrument. So the first property is that the instrument father's education does not appear in the original regression model. So the log of wage is only a function of education, and it does not depend on father's education. And that seems reasonable because in our application, say for jobs, no one is asking us about father's education, therefore it's not a direct determinant of the wage. Okay. The second property that we have here is that the instrument father's education would be correlated with the endogenous variable education so that the covariance is not equal to zero. In other words, we're going to have a relationship between education of a person and their father's education, where this delta 1 coefficient here would be significantly different from zero. And that makes sense because if you grow up in a household that the father had a higher education, perhaps the child would have higher education. So that's reasonable as a second property. And then the final property here is that the instrument father's education would be uncorrelated with the error term. So father's education here and the error term would not be correlated. So now that's why we have that father's education would be a good instrument. Other good instruments could be how many siblings a person has, because how many siblings or in the household. Other siblings may be competing for resources to get higher education. Another instrument is college proximity when 16 years old, because it's assumed that if college is closer, it's more likely that someone would get higher education. Or the month of birth. Birth may be correlated with when they enter school, and when they enter school. So these are other instruments that are proposed to be instruments for education. Now, one of the toughest choices in econometrics is picking up good instruments, and typically it's very hard to either find good instruments or justify why the instrument that someone uses is a good instrument. That's really the biggest challenge of applying the IV approach here. So again, let's assume that father's education is a good instrument for education and proceed in estimating these models. So here again, we have a regression model of log of wage on education. And let's use the OLS and IV formulas so we can find the coefficients. So the formula for the OLS is the covariance of education and log wage. So the covariance of education and log wage divided by the variance of education, right? So this is the formula for OLS, which is the covariance of X and Y divided by the variance of X. So that's the formula for an OLS coefficient. So here we have education minus education bar, which is the average, log wage minus the log wage bar, and then divided by the summation of education minus the average education and times education minus average education, that being the variance of education. So if you actually go through the data and just calculate this expression, we would be having 0.109 as the coefficient. Same thing with IV. We can find the covariance of the father's education and log wage and the covariance of father education and education using this formulas here for the covariance, basically a covariance formulas. Then we would find that this coefficient is 0.059. So what we're seeing here is that the coefficient here, the IV coefficient would be lower than the OLS coefficient. And how we are going to interpret it is that one additional year of education is associated with 10.9% increase in wages using OLS model, but only 5.9% increase in wages using IV. So notice here that what we have is we have a much lower increase in wages when we correct for this endogeneity. So just by the fact that these two coefficients seems to be different from each other, we can conclude that perhaps education is endogenous here, and that's what's leading to these to difference in these coefficients. And here we would assume that the OLS coefficient is biased and it's picking up influence from omitted factors that are in the error term, and that's why we have the effect of education on wages being overestimated using OLS here. Okay, so we did the IV coefficient using the formula. Now let's do the two-stage least squares. So here, uh, in order to do the OLS model, we are just running a regular regression, and we're getting the coefficient here, beta 1. And if education is endogenous and father's education is the instrument, the two-stage least squares would be first stage, we are running a regression of education on father's education. So this is our X, the endogenous variable from here. And then the endogenous variable is regressed on the instrument, which is father's education. We are getting the predicted value education hat from this equation right here. So this education hat would only be based on exogenous information, which is the father's education, because we're assuming that's an instrument, therefore the information here is exogenous. And then in the second stage of the two-stage least squares, we have a regression like the original regression here, but this education is replaced with education hat, which is the predicted values from the first stage. And that's how we get the two-stage least squares estimate here. So again, to summarize, the two-stage least square first stage is regressing education on father's education, get the predicted value for education, which is education hat, and then the two-stage least square second stage would be a regressing log wage on education hat, and that's how we obtain the two-stage least squares coefficient. Okay, so let me show you the results. So here what we have is the OLS estimation, then we have the two-stage least squares estimation, the first stage and the second stage of the two-stage least squares estimation. So here we have log of wages, dependent variable, education being independent variable, and this is the coefficient here. So the OLS estimation again ignores the fact that education may be endogenous and estimates this coefficient. So how we would interpret it here is that one additional year of education brings 10.9% increase in wages. Now, using the two-stage least squares, the first stage is regressing education, which is our endogenous variable here. Now the endogenous variable serves as the dependent variable. And we regress that on the instrument here, which is father's education, and we are obtaining a coefficient here. Uh, so notice that again, we have a significant relationship between father's education and education. That's good because we have a significant relationship between the instrument and the endogenous variable. So now from this regression, we are getting education hat. And now we are running again the regression of log of wage, but instead of education, we are basically getting this education hat, which is the predicted value from this first stage. And this is that coefficient here. So now notice that most statistical software, they would not call this education hat. They would actually call it education, but it would be corrected in this manner where we are going to be using education hat basically. So even though this coefficient here may say that it's the coefficient on education, it's in fact the coefficient on education hat. And so this is the coefficient here. So what we are finding here is that uh, the how we would interpret that is that for each additional year of education, we have 5.9% increase in wages. So again, notice that this is a lower effect here than the effect that we have using the OLS estimation. And also notice that this coefficient here is less significant. It only has 1 star in here versus 3 stars. And the reason for that is, again, notice that the standard errors here are much larger. And I will show you the formula for how we get these standard errors here a little bit later on. The reason why these standard errors are also larger is because of this R squared that we have that we're going to be using for this formula. So we do not have a very strong relationship here between education and father's education. Only 17% of the variation is being explained by father's education. So another thing to notice here is that we obtain the same IV and two-stage least squares coefficients of 0.059. So if you scroll back a couple slides earlier, we have the same coefficient here on IV as we have right here. And also the OLS coefficient is obviously the same, whether or not we use the formula or we're estimating the regression, we're finding again the same coefficient. Okay, so now let's talk about the endogenous variable versus the predicted values using this instrument. So here what we have is that we have the relationship and we're estimating the equation of the regression of education on father's education. So this is the first few observation of education, and this is the first few observations of father's education. And what we're doing is we're running a regression for our first stage of education on father's education. And what we're getting here is education hat or education hat here. And this education hat are the predicted values from that regression of education on father's education. So notice that we have here, so this is the actual education of the person. And if the father's education is 7, this is the predicted value. If the father's education for this person is 14, we have higher predicted value. And if it's 7, we have the same value. And if it's 3, we have a lower value here. So notice that this education hat only depends on the father's education here. And it's different than the original variable education, which may be endogenous. Here we have now exogenous variable because it's only based on instrument, on a variable that is exogenous. Another thing to point out here is that these numbers here for education hat are not necessarily whole number, so they're not. And some authors may choose to round them before they use them in a second regression. Some may use to leave them like that. So we can also have a variable that's binary, 0, 1 variable. And so if we have predicted values, then we can have, if predicted values are below 0.5, they can be replaced by 0, and above 0.5, they can be replaced by 1. So some authors may choose to round these values up a little bit to get a whole number, or most people just leave them as they are like that. But that's what it means here for education hat to only have exogenous information. It's only based on this father's education, notice here, and it's not based on the original variable here. Now let's talk a little bit more about the standard errors. So I showed you 2 slides prior that the R squared of the two-stage least squares for the first stage when we had the regression of education on father's education was 0.17. So this R squared is not very high in general. There's not very strong relationship between education and father's education. And from the regression output, we also saw that the standard errors of the OLS coefficients was this, but the standard error of the two-stage least squares coefficient was this. And so this two-stage least squares, you see, coefficient has higher standard error, and because its higher standard error was less significant. So the exact relationship between the standard errors, as we discussed earlier, would be the standard errors for the two-stage least squares for coefficient would be the standard error for the OLS coefficient divided by the square root of this R square. And so this is the expression that we have here. So we're basically obtaining um, exactly the expression that we have here. So again, if we don't have a strong relationship between the endogenous variable education and father's education that results in low R square, because this low R square is here in the denominator, what that happens is what that does is basically it inflates the standard errors of the two-stage least squares coefficients, and it makes them less significant. So again, even though we're correcting for the endogeneity, which we definitely have to do to get unbiased coefficients, the drawback is that we would have higher standard errors, less significant results. So now that was what happens when we have a simple regression model with only one independent variable. So how would we do IVs if we have multiple regression model, which would almost always be the case? So I would be repeating everything we've done so far, but it's going to be a little bit more complex because now we have a multiple regression model where we have an endogenous variable and 2 exogenous variables. So notice here that this is how the equation regression model looks like. And here y2 would be endogenous variable that's correlated with the error term. And then z1 and z2 would be exogenous variables. So for the first time here, we're not calling these independent variables x, but we're calling this variable here y2. Well, that y looks like a dependent variable. And the reason for that is that in the next presentation, what we're going to see is that sometimes we can have simultaneous equations, and that could be a dependent variable in another equation. So again, it's just a notation, but this is the same as the x variable, which is endogenous. It's just an endogenous variable. And here z1 and z2, we would call them z because to denote that they have exogenous information in them and they're exogenous variables. Okay, so now we can find 2 instruments, Z3 and Z4, for the endogenous variable Y2. So we want to have some instruments for this Y2 that are uncorrelated with the error term. And so the exogeneity conditions for the instruments are that the covariance of an instrument and the error term should be a 0. The covariance of the other instrument, Z4, and the error term should be a 0. So if we actually replace here y1 with the expression that we have up above here, this is what we're going to get. And we can again substitute the expression for y1 here. That will be the expression here. And this final equation is saying that the expected value of the error term is 0. So, we have the 0 conditional mean assumption. So that's where this is coming from. So the expected value of the error term is equal to 0. So now what we're accomplishing with these equations here is that these equations can be solved to obtain the IV coefficients, which for beta 0, beta 1, beta 2, and beta 3. Now, because we have multiple independent variables now, these expressions are going to be much more complex. And so they wouldn't have an easy solution like we had on the previous slide, but basically they could be used to obtain these IV coefficients. But because they're more difficult, people usually don't use them and apply them, and instead what people are doing is the two-stage least squares. So how would we do two-stage least squares when now we have more than more than one independent variables and potentially more than one instrument as well? So here we would have a regression model of y1 on y2. So y2 would be endogenous variable that's correlated with the error term. And then Z1 and Z2 again would be exogenous variables. So let's find two instruments, Z3 and Z4, for the endogenous variable Y2. So how would we do two-stage least squares? So the two-stage least squares, the first stage, we would call this a reduced form equation. Reduced form because we only have exogenous variables, and that would be y2, and here we would have z1 and z2. So notice the z1 and z2, these are these variables here. So these are the exogenous variables from the original model. We could still have them here because they're exogenous, so they're not going to cause any problem with endogeneity or anything like that. And here we have Z3 and Z4. These are our instruments, Z3 and Z4. So the reduced form equation has all of the exogenous variables from the original model and all of the instruments. So that's the first stage. For reduced form equation. Now from here we can obtain the fitted values y2 hat. We basically just getting the coefficients and getting this expression here. So notice one thing that we're doing here again is because Z1 and Z2 are exogenous and Z3 and Z4 are instruments, which means they have exogenous information, this Y2 hat only has exogenous information in here. If there's any endogenous part, we left it here in this new error, in this new residual here. So now the second stage of the two-stage least squares is to estimate the structural model where the endogenous variable y2 here is replaced by y2 hat. So notice that this is the original regression, and the only thing that is different here is that this y2 got replaced by y2 hat. This is the predicted value from the first stage that only has exogenous information here. And again, because this one only has exogenous information, it's not correlated with the error term. So if we just estimate this equation here, we would not, we would find a coefficient here that's not biased. Okay, so what are the properties of a good instrument? So these two instruments, Z3 and Z4, should have, again, three properties. So the first property is that the instruments do not appear in the original regression model. So as you're seeing, this is the original regression model, and Z3 and Z4 are not direct determinants of Y2. Why? Because if they're direct determinants, they should be in this equation here, and therefore they cannot serve as instruments. They shouldn't be in this original model. The second property is that the instruments are correlated with the endogenous variable Y2. The second assumption is that the instruments are correlated with the endogenous variable y2. So the covariance between the instruments and y2 is not equal to 0. In other terms, is that there is a relationship between y2 and z3 and z4, or this delta 3 and delta 4 coefficients are significantly different from 0. And again, we need that because in order for Z3 and Z4 to be serving as instruments to Y2, there needs to be a relationship between them. Otherwise, if there's no relationship, they wouldn't be a good instrument. And finally, the instruments are uncorrelated with the error term U. And again, we're not going to be testing this, but that's a property that it needs to hold. So again, That is the same as in the case of simple regression. So any good instrument should have three properties. Doesn't appear in the original equation, is correlated with the endogenous variable, and it's uncorrelated with the error term. Here we would have that the IV estimation would also be equivalent to the two-stage least squares estimation, but in the case of multiple regression, because the IV estimation is more difficult to do, most people are just doing the two-stage least squares estimation. And this two-stage least squares estimation works because the endogenous variable here, y2, is replaced in the second stage by y2 hat, which only contains exogenous information from the instruments and the other exogenous variables, and not the endogenous part that's correlated with the error term. And this is why this two-stage least squares estimation works. Now, let me give you the example. So here we have the structural equation model. So structural equation model could potentially include these endogenous variables here. And here we have that log of wage depends on education, experience, and experience square. Now we assume here that education is endogenous and experience square are exogenous. So because education is endogenous, we're finding two instruments now, father's education and mother's education for education. Now, we can always have more instruments per endogenous variable, but we need to have at least one instrument for each endogenous variable. So here we now have two instruments, father's education and mother's education. So the first stage of the two-stage least squares is to estimate the reduced form equation. Here we have education. Here, that is the endogenous variable, regressed on the other exogenous variable from the model here. So these are the exogenous variables. Because they're exogenous, they're not causing any problems, and we could use them here as well. And then we have father's education and mother's education. These are the instruments here for education. So now when we estimate this equation, we can obtain the predicted value education hat, which only contains exogenous information. And then the two-stage least squares, the second stage, we estimate the structural equation replacing education with education hat. So if you notice, this equation here is the same as this equation up here, only that education here, the endogenous variable, is replaced with education hat, which only has exogenous information in it because it's picking it up only from the other exogenous variables and two instruments which are also exogenous. And here are the results for the two-stage least squares estimation. So the first column here is the OLS estimation, ignoring the fact that education may be endogenous. So here we have log of wage regressed on education, experience, and experience square. And this is the coefficient here. So how we are going to interpret this coefficient is that for each additional year of education, wage increases by 10.8%. Now, the two-stage least squares procedure, the first stage is we pick up the endogenous variable education, which is this one, and then we regress it on the two exogenous variables and also the two instruments, which are father's education and mother's education here. And once we do that, we get the predicted values from here, which is education hat. And then in the second stage, we replace education with education hat. And then the original variables that we have here for experience and experience square. And if we look at this coefficient here, this is the way we're going to interpret it is that each additional year in education brings a 6.1% increase in wages. This is using the two-stage least squares approach. So once again, we find that this coefficient here, the two-stage least squares coefficient, is smaller than the OLS coefficient, and it's also less significant. And the reason for the less significance is that the standard error is actually higher for the two-stage least squares coefficient. Again, very similar results to what we had with the simple regression. Here we have again multiple regression where we have more independent variables, including experience and experience square, and we also had two instrumental variables. So notice again that here we have significant coefficients on the instruments. So basically that also satisfies the properties of a good instrument in terms of father's education and mother's education having a relationship with the education of a person. Okay, so now let's also consider the correcting the standard errors. So here we have if we estimate the two-stage least squares, here are the correct standard errors that we have, and here are the incorrect standard errors if we just apply uh, if we just estimate the second stage, but we do not correct for the errors, and we need for the two-stage least squares, we need to use this formula to correct for the errors, and then we have that the standard errors are higher uh, when they're corrected. So many software packages would provide the corrected standard errors for the two-stage least squares. And finally, let's talk about testing for endogeneity. So if we have the structural equation model, which is this model here, we can test for the endogeneity of Y2. So we can find two instruments, Z3 and Z4 for Y2. We can estimate the reduced form equation. So this would be the reduced form equation. Here, Z1 and Z2 are the exogenous variable in the original model, in the structural equation model, and Z3 and Z4 are the instruments. And this is like the first stage of the two-stage least squares. However, instead of looking at y2 hat, which is the predicted value that only contains exogenous information, here we would be obtaining these residuals here, which would contain the endogenous information. So if this is the exogenous information here, we would be leaving the endogenous information in the residuals. And again, the endogenous variable would be broken down into an exogenous part, which is the predicted value, and the endogenous part, which is the residuals from this regression. And we can now estimate the structural equation model with the residuals here being part of this model. So we could go back, re-estimate this model here with the residuals, and then look at this gamma 1 coefficient. So now if that gamma 1 is not significantly different from 0, we would have exogeneity. And if it's significantly different from 0, we would have endogeneity, because we would have some endogenous part here left in the residuals. So that would be the test for endogeneity. Okay, so applying it to our example, here we have, this is the structural equation model that we have here. We would test for the endogeneity of education with two instruments, father's education and mother's education for education. And we would be estimating the reduced form equation with the exogenous variables here from the original model and the two instruments. We would be obtaining the residuals from this regression here that would contain the endogenous information. Uh, and then we would be estimating the structural equation model again with these residuals here are put in the structural equation model. And we would have the case where this coefficient here is not significantly different from 0. We would have exogeneity. And if it's significantly different from 0, we would have endogeneity. So, so here is the model again. And everything would be the same up to here. So here, this is the structural equation model that we have. Then we have the reduced form model education regressed on the two exogenous variable and the two instruments. And what we're going to be doing here is, instead of actually getting the education hat and putting it here in the structural model, we would be getting this residual hat here, and we would be putting this residual into the structural equation model. And we would be looking into this equation here, looking into the coefficient on this residual. And we're seeing that actually this coefficient here is significant. And so that is the information that is the endogenous part here that we have of the that is in the residual. So again, um, when we're breaking down the endogenous part, we have education hat, which would be containing the exogenous information, and that residual will be containing the endogenous information. And so because this coefficient here is significant at the 10%, we would conclude that the variable education is endogenous. And because this education is endogenous, we would need to be using instrumental variables to correct for endogeneity. So to summarize this presentation, let's review a few concepts. First, describe the three properties of a good instrument, describe the IV estimator, and describe the two-stage least squares procedure with first and second stage estimation, and then finally describe the test for endogeneity of an independent variable. Thank you for watching.